Hi everybody, welcome to another video in Precalculus section 4.2. One-to-one functions and inverse function. Once again, this is just a review of what we already have in coarse algebra and trigonometry. So, a one-to-one function. A function is one-to-one if two different inputs in the domain result in different output in the range. So that is, if x1 and x2 are different, then f of x1 is not equal to f of x2. So I will write that as x1 not equal to x2 implies f of x1 not equal f of x2. Or logically, this is equivalent to saying if we have f of x1 equal to f of x2 implies x1 have to be the same as x2. So it will be either one. They are logically equivalent. Right. So pretty much if we have different x, we will have different y's. Now determine the following is one-to-one function. So I have the a's and then the HDL. So first of all, when we look at this, they have 1, 2, 3, 4, 5, and then says 4. So they will not be one-to-one if the numbers do not match, because we have 1x and 1y and 1x and 1y. So if we want one-to-one function, the number element in the domain and number in the range must be the same. So they're not the same, so they're not one-to-one for that reason alone. But according to definition, we have both of them go to 35. We have the 53 going to 35, and then also the 41 going to 35. We cannot have that. Different x values have to come to different y values. It is a function, yes, but not a one-to-one function, because two different x values produce in the same y values, so it's not one-to-one. So we just say this is not one-to-one. Right. The way if we have the graph, then we can use the horizontal line test. The horizontal line test to test a function. If we draw a horizontal line, and if we cut the graph more than one point, it is not a one-to-one function. So this is not a one-to-one function, because the horizontal line here cut the graph at 2 points, so it's not. Same thing here, we have an example. We have the graph of y equal to x to the 6. Y equal to x to the 6. We see here there's a horizontal line intersect the graph at 2 different points. So this is not one-to-one. So this is not one-to-one. Because different x values produce the same y values. Cannot be the case. And it fails the horizontal line test. Similarly, we have a bunch of horizontal line, and all of this only intercept the graph at 1 point. So in this case, y equal to cube root of x is a one-to-one function. Y equal to cube root of x is one-to-one. Next, if we have the function that is increasing on interval, then in that interval it is one-to-one. If the function is decreasing on an interval, then that is one-to-one. Have to be very careful though. We just said by increasing we mean it cannot be. In calculus they have the different definition. When we mean increasing, we have to go increasing. When we write like that, this is called non-decreasing, which is different than increasing. Because non-decreasing could be increasing or constant. We're not talking about this. The constant function will fail the horizontal test for sure. So it cannot be a constant function. So it can only go up like this, and that is increasing. So be mindful of that. Besides increasing and decreasing, we still have constant. We cannot have constant as a one-to-one function. Right. So that pretty much is one-to-one function. We need one-to-one function because when we have 1x give us 1y, then we can get 1y give us back to that 1x. So in that case we have the inverse function. So only one-to-one function has inverse, and we say suppose if f is a inverse, it's a one-to-one function, then each x in the domain there's exactly one y in the range, and correspondingly each y in the range there will be exactly one x in the domain. So 1x, 1y, and then 1y give us back that 1x. And the inverse function denoted by f to negative 1, but for this we just say f inverse. Right. And look at this example. Let the domain the function represent some certain state, and the range represent the population. So I'm not sure how old is this textbook, so this might be the old information. Right. So we have the state and population, and this 5 states, 5 different numbers for population, and each one of them just go one-to-one. So this is the one-to-one function, and it certainly has inverse. So the inverse is we get the numbers from here going back to the state. So that exactly. So this is the function, and we can say this is the inverse, or we can say this is the function and that is the inverse. Of course, when we say f is the inverse of g or g is the inverse of f, actually we should say f and g are inverse of each other. Right. Right. So f is the inverse of g, then g is the inverse, and g is inverse of f, or we just say f and g are inverse of each other. Right. Find the inverse of the following function. Right. First we check all the element in the first entry in the domain, -3, -2, -1, 0, 1, 2, and 3. It is a function. Now, is this a one-to-one function? Look at the y values: -15, -10, -5, 0, 5, 10, 15. Oh, that's good. So we have one x and one y. So in that case, if we want to find the inverse, it is very easy. We just reverse the x and y. I mean, reverse the components. So the inverse, let's say this is the function, then we can write the inverse as follows: -15, -3, -10, -2. I just interchange the entries. So that is the inverse. Of course, state the domain and range of the function the inverse, well, we run out of space. But what we see here is, since we interchange, what we can say is the domain of the function is the range of the inverse, and the domain of the inverse is the range of the function. So because we're just switching between the x and the y, between the domain and the range, to get the function to the inverse from the domain to the range, or from the range to the domain. And we have the function and the inverse. Right, because of that, if we have start from a point x, take the function, we'll go to y, and take the inverse, we will go back to x. So the inverse, the composition of the inverse of the function is x, and the function of the inverse is x. We can take this put together as a definition of the inverse if we want to. Some other books, this is the definition of the inverse. If the function is one-to-one and we have these two, then they are inverse of each other. Right, so this is what we have here. Yeah, so we start with x, apply the function to get y, apply the inverse, we get back to x. Right, now let's verify that g of x and g, we use the notation for inverse already, but it's just so that they are inverse of each other. So we need to do two things. The first is that g of g inverse of x must be equal to x. And then the second, because g inverse of g is equal to x as well. So we do g of g inverse. The function g is something to the fifth. That's what the function g is. And then the inverse is the fifth root of x. And the fifth root and the 5 power cancel out. We have x. So yes, so that's check. Now the second one, of course, we need to check is the g inverse of g of x also equal to x. So we start with the g inverse, which is the fifth root of x. I should not put x there, I'm sorry. The fifth root of something. Whatever I put in the parentheses, it must be the same. Now I can put g of x here. And then over here I can put x to the fifth. Because x to the fifth is the same thing as g of x. And then they will cancel out and give us back to x. So that check. Yes, so we can say so g of x to the fifth and g inverse fifth root of x are inverse of each other. Right. Now, I want to do a little more general. The root and the power, because if they are the same, they will cancel out. The way we can write that is we can use this property. When we write like that, we mean the power will be on the top and the root will be at the bottom. Or if we write like this, it could be m root of x to the n is x to the n over m. So power on top, root at the bottom. In this case, both of them result in, just look at this one, it would result x of 5 over 5, which is x to the first, or x. Right, so indeed they are inverse of each other. Right, with another example. By the way, to check for inverse, we need to have both of them. Right, verify that this function are inverse of each other. Well, again, two things. F of f inverse of x is that equal to x. So we have f of f inverse of x, but like I said, we start with the function f first. Instead of x, I just leave the parentheses like this. Doesn't matter what I put in the parentheses. If I put whatever I put in the parentheses, they have to be the same. That's what a function does. Right, now instead of that, I will put the inverse. And the inverse will be the same as this. 1/4 x plus 7. Now, 4 and 1/4 cancel out. We have x plus 7 minus 7. 7 and 7 cancel out, we have x. That check. Next we have f inverse of f of x is that equal to x. So we start with the inverse first, the outside function. Inverse function is 1/4. Instead of x, I'll put the parentheses. Whatever I put in the parentheses must be the same. Now in the parentheses is f of x, which is 4x minus 7. That's what we have. So we have 1/4 4x minus 7 plus 7. 7 cancel out. 1/4 times 4x. 4 and 4 cancel out. We just have x. And so that check. Because both of them are satisfied, we say the f and f inverse are indeed inverse of each other. Yeah, we need to have both of them. Right. Now, the graph of the inverse function, because we interchange the x and y, what in the function and inverse, the graph of the function and the inverse will seem symmetric on the line y equal to x. So let's just graph this two and see if it is the case. For x minus 7, one-fourth, or if we want to just say 0.25 times x plus 7. Right. So those graph, if we want to look like perfect symmetry, so prefer to go to hit zoom number 5. So in that case, the x-axis and the y-axis will have the same increment, the same length for each increment. For some reason it is frozen. Graph. Okay. So those are the two functions. If we graph the line y equal to x, because you see these two graphs are symmetric on that line. So that's good. Right, now, so we certainly can verify if the functions are inverse of each other. We can look at the graph. It's not as good as we can verify that algebraically. The combination of the function and inverse must be x in both orders. Right. Now, to find the inverse function, so for y equal to f of x, to find the inverse, we interchange x and y to obtain x equal to f of y. If possible, we solve for y to obtain y equal to f inverse of x. Right, so those are the steps. Of course, we can check using the graphs or by the definition of inverse. We're going to do both. Right, to define inverse, first we'll replace f of x by y. So f of x by y. And the two most important steps in finding the inverse is interchange x and y. So if x equal to 3y minus 5. And now we solve for y. So to solve for y, first I move the 5 over. That becomes a plus. And then divide by 3. So we have y equal to x plus 5 divided by 3. And now we just replace with the notation. Y will be replaced by y f inverse. Just get the proper notation. right? So yeah, simple enough. That's how we find the inverse. Now check by verifying indeed they are inverse by the combination of the function and the inverse. So we're going to check both of them. F of f inverse, is that equal to x? So we start with the function. The function is 3x minus 5. So we're going to have 3 times something minus 5. And that something is the inverse. What we did find is x plus 5 over 3. 1. Cancel out the 3. We have x plus 5 minus 5 equal to x. And yes, indeed it is. And then next we check for f inverse of f of x equal to x. So we have the f inverse is this function. So we're going to have replace the x by the parentheses. Then whatever we put in the parentheses will be consistent. They must be the same. F inverse of f of x. Now if we put f of x here, f of x is 3x minus 5. So we do that, we have 3x minus 5 plus 5 over 3, and negative 5 plus 5 cancel out, 3x over 3 plus that x. So that check. So indeed they are inverse of each other. And finally by the graph we can confirm them. So the first function is 3x minus 5. And the second function, x plus 5 divided by 3. If we look at the graph, indeed they are symmetric on the line y equal to x. Right, so if we want to graph them, now let's focus on the graph. Okay. So these two columns then. F of x equal to 3x minus 5. This is an equation by line, so it's very simple. We just make a table for x and y. Let's choose some values. When x equal to 0, y equal to negative 5. When x equal to 2, x equal to 1. We want to choose the numbers a little bit apart. So in that case, we don't have 2 points, that's too close. Usually when you try to draw a line, it is better to have 2 points apart so we can connect them. Like when it's easy to draw when we have 2 points, that too close. And we use the ruler, it's more difficult that way. Regardless, 0 we have 2. 0 we have negative 5, sorry. And when we have 2, x equal to 1. So this is the equation of the original function. Right. Next, let's look at the inverse. X plus 5 divided by 3. X and y. Now I'll choose some values. I will not choose 0, because if we choose 0, we have 5 or 3. It's not a nice number. We choose some x values so that it will come out nice and even. For example, if we choose x equal to 1, 1 plus 5 is 6 divided by 3 is 2. So x equal to 1, y equal to 2. Or we can just switch in the x and y here, right? Because if we choose x to be negative 5, then y equal to 0. We just interchange x and y. That's what the inverse does. But of course, we don't really need to do that. Let's choose different values. like -2, -2 here, plus 5 is 3, divided by 3 is 1. So x equal to -2, y equal to 1. And so we have the graph of the inverse. And because in this they are symmetric on the line y equal to x. So yes, we can confirm based on the definition or that whatever that theorem, that property says, or we can confirm by the graph. But the graph, of course, it's not as good as the using the definition. Right. Now, find the inverse of this one-to-one function. All right, so we don't have to confirm it, but in this case, just go ahead and find the inverse. Right. So, suddenly a little dark. Anyway, so to find the inverse, first thing, of course, we'll replace f of x by y because it is easier to interchange x and y. Just trying to simplify the notation here. Alright. So now the first step, of course, was interchange x and y, and then we solve for y. Do that, we have x equal to 1 over y plus 2. Next step is to solve for y. So we can make a fraction here. X over 1 equal to 1 over y plus 2. We can cross multiply xy, x times y plus 2 equal to 1. And multiply it out, xy plus 2x equal to 1. Subtract 2x on the other side. And then just divide by x because we need to solve for y, right? So y equal to 1 minus 2x over x. And finally, the proper notation, instead of y, we're going to use f inverse x over 1 minus 2x. Alright, let's look at the graph. One divided by x plus 2. And then the other one, we have x divided by 1 minus 2x. Right, let's see. So that is the function. And that inverse. Yeah, kind of difficult to see if they are symmetric on a line y equal to x. But if you see this line and this line, by the way, zoom number 5, it will look better. Yeah. So if this line, that line is symmetric, and that part and that. Okay, let's look at the graph again. Okay, you can just turn up one of them. So that inverse, so we have that portion here. Now let's just grab the first one. we that's a good thing we check, right? This is a function. For some reason I just flipped them for no reason. Sorry about that. So I guess that is the point of checking. Sorry, we still have 1 minus 2x over x. Sorry about that. Right. Now, let's grab the inverse first. So we have this portion here. Actually, maybe zoom number 6 is better. Okay, so we have that portion here. Just focus on this part. It should flip over there. Now let's turn that off and look at the function. So we have that, and now let's grab both of them. Right. Now it is better to see that this portion and this portion are inverse of each other. We have this portion and that portion are inverse of each other. Reflection of each other. Oh, is it better? Yeah, this is better. Yeah. Right, sorry about that. Right, now find the inverse of this one-to-one function. Just find the inverse. First, replace that with y. And then interchange x and y. And then you can solve for y. Then we cross multiply. Right. Now we'll solve for y. I'll multiply all out xy minus 2x. Now we have y on both sides, so we need to move them to one side. And then we move the 2x to the other side because we solve for y. We don't need x. Both of them have y here. Why don't we factor it out? When we factor out y, we have x minus 1. And then to solve back, to get y by itself, y equal to x plus 1 over x minus 1. And the proper notation for the inverse, f inverse instead of y is equal to x plus 1 x minus 1. Right. If we want to, we can use the graph to verify it, to see if they are symmetric. First one is x plus 1 divided by x minus 2. And then in the function we have 2x plus 1, the inverse, 2x plus 1 divided by x minus 1. Yeah. So you see there's a symmetry here and here. Right, so that's good. Next, I'll find the inverse of the function x squared plus 2 for x greater than x. Oh, there should be a typo. So let's just say for x greater than 0. And you know why is that? Because if we graph the function, I'm just gonna turn this function up when we graph it. Now so we clear this function, clear that function. Right, let's graph x squared. And that certainly failed the horizontal line test. X squared is not 1 to 1. Sorry, we have x squared plus 2 still. Yeah, just put x squared plus 2. Still, it's not 1 to 1. So it cannot be, it will not have an inverse if it is not 1 to 1. So in that case, we only look at when x greater than 0. So I think we did this way back in chapter 1, I think. Or chapter 3, I don't remember. But if we want to graph with the condition, we just divide by x second math, and that is greater than, just it can be equal to, greater than or equal to, right, to 0. And we have that graph only on the right side. Right, quickly, because x greater than 1, x greater than 0, we have the values of 1 or 0, because that is logic. I just want to mention this real quick. Where we have 1 greater than or equal to 0, this will give us 1 because it's true. If I have a negative 1, that will be 0 because it is false. So if it is true, it is 1. If it is false, it will be 0. Can only have those two values. Now, we have this function divided by 1 itself, which is good. Divided by 0 is undefined. So that's why it will not graph anything when this is equal to 0. It will not graph when this is false. It only graphs when this is true. And that's exactly what we want. So yeah, just keep that part there. Right, now we find the inverse, like what we have been doing. Replace this with y. We'll keep that in the back pocket later. X squared plus 2. Right, replace the function f of x by y. Next, to find inverse, interchange x and y. So x become y and y become x. And now we can solve for y. So we solve for y, subtract 2 on the other side. And then we take the square root on both sides. And very important that when we take the square root on both sides, what do we need to have? Plus or minus. So we have plus or minus square root of x minus 2 equal to y. There's a problem. Do we choose a plus or do we choose a minus? So right, now to do that, let's just go back to the original problem. For this problem, original function, what we say is that the domain for this problem, of course, x greater than or equal to 0. Right? So we can say x greater than or equal to 0 if we want to. Or if we want to, we can just say it will be from 0 to infinity. and then the range. If we look at the graph, it is greater than or equal to 2. Or we can say it goes from 2 to infinity. So that's what we have. Is this is for the function. So if that is the function, that's what we have. Now, in the inverse, for the inverse, do we choose a plus or do we choose the minus? Well, one thing for sure, if this is the case for the function, we will know for sure for the inverse. The domain of the function is the range of inverse. So if I want to have the domain of the inverse, will be the range of the function. So which is, we go from 2 to infinity. The range of the function is the domain of the inverse. And the domain of the function is the range of the inverse. So we just switch those two. Yeah. Domain and range becomes range and domain. So we just flip them. So we know for sure that is what we have for the inverse. In which case the range is from 0 to infinity. Because of that, it has to be positive. It cannot be the negative. Of course, the domain will be that, which is perfect. Right? So, yeah, because the function is not one-to-one, we have to restrict the domain. So it is one-to-one. One-to-one function, we have the inverse. But when we do that, we have the plus or minus here. And we have to, based on the domain and range, to choose that it has to be the plus. So the domain and range will satisfy those properties. Right, and then finally we graph them. That should be simple. X squared plus 2. We have this. So this is the function for x greater than or equal to 0. And then we have the inverse. Square root of x minus 2. Well, that's easy, right? So this is inverse. Square root of x minus 2. And the graph of the function and the inverse must be symmetric on the line y equal to x. So if we draw a line y equal to x, the graph are perfectly symmetric. So that's good there. Of course, if we have the part of the x squared that is negative for negative x, if this is the case, they will not be symmetric with this part. So in that case, it doesn't have that. Right. So be mindful when we solve for, when we square, take square root of both sides. That could be plus or minus. Right. And finally, I put all the properties of the one-to-one function here in the summary. The function is one-to-one. Only one-to-one function has inverse. We can interchange the domain and range to get the function to the inverse. And by definition, the combination of the inverse and the function gives us back to x. And finally, the graph of the function and inverse are symmetric on the line y equal to x. And this is how we solve for the inverse. Interchange x and y, and then solve for y. And with that, I end section 4.2 here. As always, thank you for watching, and see you in another video in pre-calculus.